Hello, it's James from XRobots.co.uk. This is part 14 of my Ultron, the real robot build, which is a real robot. There's no one inside, it's not a costume, and this is going to be driven partly by a motion capture suit and its own AI. So I've got some things to do there in terms of control. So far I've mostly been doing some mechanical design, as you can see. So I've got most of my main shoulder axis in and also the ab actuators. Early on I did some R&D on the mechanisms and also built the motion capture suit we're going to use, so go back and look at those first episodes to find out what this is all about. Today we're going to try and make it move, so I need to put some position feedback at least on the joints. Hopefully we can get some code done and get some power into it and see what happens. My three main shoulder axes are this one that moves the shoulder backwards and forwards, this one that rotates the upper arm, and this linear actuator here, which lifts the arm up. So have a look back for the previous mechanical builds to have a look at those, and also look at part 3 when I built a small-scale test arm using servos and drove it with the motion capture sensor. And this robot is built to inherently use Euler angles, which are a bit different to absolute orientation, or real-world angles, shall I say. So each one of these as well has this sort of split part which rotates independently, and I've got that in all of them, which at the moment makes the joints a bit loose. And the aim is that in there is going to be a squashy piece with some force-sensitive resistors that allow me to read feedback on those joints. And there's also one in here, so I've got 3 joints and 3 feedbacks for basically collisions or if someone pushes the robot, so it's going to be quite a social robot that people can interact with. Those sensors I'm not going to try and wire in just now because I can't really do it until I've got the rest of the load on the arm. And I can't really tune up how squashy those things need to be. I need to put something in there for now to get rid of the slack, but those sensors are going to come higher up the sensor chain with the other sensors on the robot when I get to build its AI and its separate brain, which I also discussed in part 1. So I need to put feedback for position on these though, so we need some potentiometers at least. It's fairly easy for the rotational axis, but the linear slider here is a bit more challenging. The 2 main linear actuators are basically gate actuators with an 8-inch or 200mm stroke. So obviously they slide right out and they lift these shoulders up. I've also got 2 other actuators in the front. If I just take those away, you can see these screw threads, and those will move this plate around, and it hinges against the back on a Ninja Flex spine and another bearing, so that can tip this way and also backwards and forwards. I'm going to ignore those for now. I'm going to get the feedback working on these linear sliders before I decide what to do with these. I only really need to use these if I drive the arm past a certain distance and I need more lift, and then I can skew the whole upper body to make that arm lift up even higher. So for most of the joints, as I say, it's easy to put a potentiometer on, but these are going to be rather harder to do, and I can't really break into them now to get any sort of encoder up higher on the gear train. Before I started messing around with encoders, which obviously will need a home position before they can start counting, I decided to actually see if there was such a thing as a 200mm potentiometer, and I found there was, in fact. They didn't look like traditional slide pots out of a mixing desk. They look like this. They're self-adhesive with some 3M backing. They've got 3 terminals, as you'd expect for a potentiometer, both ends of the resistance and the wiper. And basically they're quite cheap. I think they're £6 or £7 each. I found them on eBay. You can get them in multiple places globally, it would appear. So there's obviously no knob to slide up and down, but you can pretty much use anything as the wiper. So you stick this down and then you just run something up and down it. So I've connected one up here to 2 of the pins, what will be the wiper and one end. It's a 10k potentiometer, so I've connected my multimeter up there. So now if I just go and touch it somewhere, it should give us a resistance. So roughly in the half, halfway should give me about 5k. As I slide up and down, it goes all the way from 10 and all the way down to almost 0. It does give me infinity when I let go, but that's a similar problem to the force-sensitive resistors, so I could probably do with some other resistors sort of in parallel with the 2 halves, but we'll see how that goes. So now I just need to make a reliable wiper, and I think you can use pretty much anything to wipe on there. I fancy something that can apply pressure but won't cause too much friction, although the gate actuators of course will probably overcome it. So I was thinking about a wheel that runs up and down with a Ninja Flex tyre on it, 3D printed, and then I can get the absolute position of those actuators wherever they are from power up or at any point. So now the challenge is just mounting this and mounting a wiper that reliably runs on it. The The plan is going to be to stick this on here with its self-adhesive strip down the outside. Then from the top, which extends outwards, I've got obviously the bolt on the actuator that's attached to the robot, and that's going to operate, or at least have a fixed thing that starts at the bottom, and as this extends, obviously that wiper will come to the top. I've been experimenting with this, which is a bearing I've glued a very small Ninja Flex tyre on, which is going to run up and down, but obviously it's going to be quite hard to keep the pressure against there. So instead what I've decided to do is I've been testing the angles off the side of this. So basically make a piece that fits on the side that will be obviously longer than this and run the entire length. And that's going to have a groove on its inside surface. And I think what I'm going to do is actually just have a plastic rod that slides in there with a Ninja Flex wiper. So it's a bit like the tyre, only it doesn't rotate. The problem with this, of course, is that if I stick it in the groove, the tyre doesn't rotate on the inside and outside in the same direction, so I'd have to have a pair of them next to each other, rotating like that to run in the groove. So I think I'm overthinking it there. Probably just something that slides in there will be fine, with a kind of spongy bit that presses on the resistor here. And you don't need to apply much pressure to make this work, so we'll have to see how reliable that is. As long as if it comes off and this goes to infinity, these shoot to the bottom rather than shooting to the top and crushing the robot in the middle, then it'll be okay. I've been experimenting with the wiper, and in fact what I've got is some of this foam, which is shiny on one side and it's self-adhesive on the other, and it's quite squashy. So I've made this little wiper which is 3D printed with a bit of that foam stuck on, and obviously it's got a kind of squashy piece there to apply pressure as well as the squashiness of the foam. And that seems to work quite well as I slide it up and down there. So the back end of this is curved, and that fits into a groove that I've now printed on this longer bracket, which was the same angle as the little test one. So it can slide up and down like this. So we'll get this stuck on, we'll get that stuck on. I've already soldered some wires to it now. And we'll see if that gives us a reliable reading sliding up and down. Hopefully you can see that I've glued the linear pot strip in there, and I've got my wiper now mounted, which can slide up and down. So if I just zoom out, you can see the multimeter display, and you should be able to see that that works pretty reliably as I push it up and down, that I get a resistance between 0 and 10k. So that seems to be working pretty well. So now I just need to attach the studding onto there and make a little bracket to attach it to the top point, so that obviously as this extends, it slides this up and down. I've made a little bracket on each side there, which just holds that bit of 4mm studding, and it goes onto the same bolt that goes through to hold this into its bracket. So now, of course, as the actuator slides up and down, my little wiper slides up and down. I've got the meter connected there to measure the resistance, and I'm just going to power up the motor and extend that out, and we should be able to see that changing. There we go, so we got down to 5.8k and all the way back up to the physical end stop and the end switch at 9.7. So obviously this would go further if the plate were to tip, as I demonstrated when I built this, and we can get almost to the top of this by tipping the whole robot over, but the feedback seems to work okay. So now we've got basically a servo, so we can measure the position feedback and we can drive the motor to a demand position in each direction. Now we need to actually make that into a servo, so we need something to read the position of the joint, the demand position, which for now is going to be another pot that I turn. Eventually it will be data coming off the motion capture suit and the robot's AI. And we need something to drive the motor and then some sort of loop that tries to close the gap. So I'm going to start with these, the BTS 7960 motor drivers, which are quite high current. There'll be one of those for each motor, of course, and including the abs and the elbow, there'll be 5 main motors per side, so I'll need 10 of these. This is the L298, which I don't think will source enough current. Even if you parallel up both of the channels, you still only get 4 amps, whereas this goes to 40. Without the arm on, I can't really tell how much it will be, so I'll have to build the whole thing and measure it. I might get away with this for some axis, but I suspect I'll need these. Then we've got some Arduinos, so I could make a distributed system, a bit like Hulkbuster, with serial nodes mounted around, each one dealing with a joint. Or I could just about control each side of the robot with an Arduino Mega, which has got enough analog ins for all of the position sensing and enough PWM outs to control well, it's got a lot, about 12 or 13. I only need 10 to drive those 5 motors in 2 directions. So it could be more distributed than that, so I could use those for the arms, then another normal Arduino for the head and some other bits and pieces. So we'll see how that goes. For now I'm going to use this, and we're going to just try and make that into a servo. So I've connected the wires, both for the motor and the wire here that comes out from that strip, to my Arduino. So let's take a closer look at what we've got there. So they recommend putting a 10k resistor on the end of that pot. Normally you connect one end to 5 volts and one to 0, and the wiper would give you the analog value, but they actually say you shouldn't connect it directly to power. So that's from the manufacturer. So I've got 2 10k resistors on the ends of them and the wipers in the middle. And I've also got my demands pot, which is just connected to 5 volts and ground, and of course the wiper is another analog value. So I've got my 2 analog ins come into the Arduino there. And at the moment I've just written a little bit of code so I can print those to the serial terminal and see what sort of values I get. Obviously with the 10k resistors I don't get the full range there, I only get between 1/3 and 2/3 of the value, but I've got 10-bit resolution, so that should be enough numbers for the amount I need to move the robot. Here's my really simple Arduino code, which is basically just reading those analog ins and printing them to a serial terminal, and you can see the values there. So for the actual position and the demand position. So if I now turn the demand pot, you should see that value change. And if I now run the motor, then you should see the actual position change. That's all the way up and back down again. I've now added the motor driver in, and that's connected to PWM pins 5 and 6, and the battery is connected and the motor is connected, so now I can drive that motor in whichever position based on the demand pot. I've implemented a simple PID controller from the PID example from Arduino Playground, and this is the same code that drives BB-8 and lots of other projects. So I can tune up here the input, the output and the set point. And in this case the input is the actual position, so the actual position, the set point is my demand position, the output of course drives the motor. So a lot of this stuff is just the PID setup on the variables, but basically what I've done with those 2 inputs is some mapping. So I've actually mapped the actual position between 341 and 682, which is 1/3 and 2/3 of the value, and that's because of those 10k resistors either side. And then I've remapped it to ±255, and if I was clever I could have done that in one go, but this is much more readable and I can remember what I've done. I've mapped the pot as well for the demand to ±255. My serial stuff for debugging is commented out, and basically I've said my input to the PID is the actual position and the set point there is the demand position. So simple as doing PID compute and then driving the motor in either direction depending if the output is above or below 0, and I always turn it positive there to drive PWM by using the ABS statement, and obviously if it's nowhere, if it's in the middle, then it should stop the motor, although that should never happen because it's always going to be equal to 0 or less than 0. There's nothing in between there because I'm using integers. So let's see what that does. Right, let's give that a spin. So I've got my pot down here I can turn, and we should find the result of the PID controller is the proportional response. So as the arm gets close to its position that I'm demanding, it will start to slow down so it doesn't overshoot. And these actuators move pretty slow anyway, so I probably could just turn the motor on and off dead, but we get quite a nice smooth effect there. So I'm going to put a bit of load on the arm as well, as if the rest of the arm was connected. I probably need to tune this up again when it is, but let's just turn that knob. And that starts to decelerate as it gets there. Just go down a bit. Just turning the knob there a little bit at a time. So yeah, that will need tuning some more. At the moment the D, which gives it a tighter response, is set to 0, so it's purely P. That seems to work okay. I can move the arm up and down quite well. I could smooth out the data from the pot as well, which is what I did with BB-8's head. So it accelerates away rather than going full speed if I turn the knob a long distance. And we can model all of that data and put proper acceleration and deceleration on. which probably we'll need from the motion capture sensor so we don't get jitter. If you look back on part 3, that response was quite jittery because the data wasn't smoothed. But yeah, pretty happy that that's okay. It's got quite a lot of ability to pull load on there. It's easily going to lift its whole arm up. So there we go. Now we need to work on the other 2 joints and turn those into servos as well. My other 2 axes that we need to put feedback pots on are of course these, which bring the arms backwards and forwards, and the one that rotates the arm there, and that makes up all 3 shoulder axes. Now these are split in 2 halves, so the bottom and top rotate independently. And as I said, there's space inside to put some squashy stuff and some force sensitive resistors. But for now I'm not going to do the force sensitive resistors. I'm going to come back and do that when I do the sensor inputs. And that goes higher up the AI chain. So for now I'm just going to take one of these to pieces and stuff some sort of dense foam in there to stop that. Otherwise my servo won't respond properly. Here's one of those units, and the slots are intended for the wires to come out for force sensitive resistors. So inside there's some space there, and obviously some squashy stuff will go in there so I can tune the response mechanically of how squashy it is to get feedback on the load. So for now I'm just going to stuff some stuff in there, probably some foam PVC board to block that nice and solid, and I'll come back later when the arm mass is on to tune up what actually goes in there. For now I just need to make that joint rigid. Now I've blocked out those things so they're nice and rigid. I've fitted this pot in the bottom and it's fitted in line, and it's got a little thing here which detaches, which goes on the outside. I've got the other one here. So it goes into a kind of socket that I've solvent welded on the bottom that the pot will push into. And I'm using these pots with a split in and serrations, so that will grip in there. So that will push in, and then the other piece on the outside solvent welds onto the bottom of this. There's another little piece which screws on so I can remove this bottom part when I want to get this out again, and then I can just pull the pot out and everything comes away. So now if I rotate this, you can see this pot rotates and it gives me the angle. I've also mounted a feedback pot for the outer arm, and that's fitted to a rod that comes down the back from the stationary part, and I've basically sawn off that studding that came down. And of course this is in line as well. I haven't fixed this piece on yet. It will be solvent welded onto the bottom of there when I've decided exactly what orientation it should be. Obviously I've got those 2 holes there for 6mm studding to come down, which is where the lower arm will fit, and I really need to design that before I fit that feedback pot in place, but again that will function like a servo. So I've just set up the PID controller again with the Arduino, which I've got down here with this axis. I'm not going to bother with this one because obviously the pot's not fixed on, there's not much to see until the arm's there. But if I now turn this, we can see we've got quite a range of motion there, and I can control it quite accurately by turning the knob. Some deceleration but no acceleration yet, so it does just move full speed, and you can see the whole thing wobbling, which eventually if I manage those acceleration and deceleration curves properly, that should go away. We've got quite a range of motion there, which should be more than enough. So pretty happy with that. Pretty happy with the strength of the motor. Even when I run it slowly, it seems to shift the arm with not too many problems. So I think that's going to be okay. I'm pretty happy with how that joint feedback works. The linear slider pots are pretty good. I need some more for the ab actuators, which are also obviously linear sliders, and those are 100mm length, and there is a 100mm version of that self-adhesive slide pot. So hopefully I'll be able to use those, but I'm going to see how the ones I've got work out and how my wiper design works before I go and buy them in case I have to do something else. So next time, hopefully I'm going to get at least one arm and possibly the head driven by the actual motion capture stuff, which is currently being modelled by Morris the mannequin. So have a look back for the early parts for that. And if you want to see why my axes look like they're in weird places, then as I say, don't forget to check out part 3 to see the test arm in action and find out why I've structured all of the mechanics the way I have here. And in fact, I do control this from one sensor off the arm of the motion capture suit. So hopefully it should just be a case of translating that onto the axis of this. So don't forget to subscribe for more updates on this project and other projects. Also check out the social media links in the description of this video, including my new Instagram account for sneak peeks and updates of other projects. That's all for now.